Let's read the question. We have a triangular piece of cardboard, M, F, H. In part, we derive the cosine rule for the side M, H. Then the cardboard is fitted snugly inside a box, and we use its measurements to find some angles and an area. Here is what the box gives us. Length 12, height 5, depth 9, and M sits exactly halfway along the top edge AB. And here is everything we must do. Derive the cosine rule, find the angle at F, sketch the alternative triangle, then find its top angle and its area. So here's the plan. The box is 12 by 9 by 5, and M is the midpoint of the top edge. We derive the cosine rule, find an angle, sketch a second triangle, then finish with its angle and area. Part A, here is the triangle M, F, H, the side opposite F, which is M, H, we'll call F. M, F is H, and H, F is M. The angle at F is just F. The trick is to drop a straight line from M down to H, F at a right angle at a point X. That splits the base into a short piece X, and the rest, M minus X. Let's keep the triangle beside us and work it through. Step 1. Look at the small right triangle on the right, MFX. The cosine of F is the side next to it, X over the longest side, H, rearranged, X is H cosine F. Call that equation 1. Pythagoras' theorem links the three sides of a right triangle, so we use it here. In that same triangle, the height M, x squared is h squared minus x squared. That's equation 2. Step 2. Now use the big right triangle MHX. By Pythagoras here, M, h squared is the height M, x squared, plus the base M minus x squared. We already know M, x squared from equation 2, so swap it in. Expand the bracket. The plus and minus x squared cancel, which is the whole point of the construction. Finally, replace x with h cosine f from equation 1. And there it is, the cosine rule. With the side names, that is m, h squared equals m, f squared plus h, f squared minus twice m, f times h, f times the cosine of the angle at f. Part B1. Here is the box, 12 long, 9 deep, 5 tall. The cardboard sits inside it. M is the midpoint of the top edge AB, reaching down to the corners F and H. To find the angle at F, we first need all three sides of this triangle. Let's keep the box beside us. The side H, F runs across the bottom of the box, a diagonal of the 12 by 9 base. By Pythagoras, 12 squared plus 9 squared is 225. So H, F is 15 centimeters. The side M, F lies flat on a face. M is 6 across from the corner above F and 5 down. 6 squared plus 5 squared is 61. So M, F is the square root of 61. We'll keep it exact, not rounded. The side M, H cuts right through the box. Drop M straight down to the base at X. M, X is the height 5. On the base, the distance from h to x is 9 and 6, so x squared is 117. Then h squared is the height squared plus that, giving 142. So h is the square root of 142. Step 4. Now we have all three sides, so we use the cosine rule we just derived. The angle we want, at f, sits between the two sides m, f, and h, f. Drop in the three sides we found. Tidy the numbers. Rearrange to get the cosine of the angle on its own. Take the inverse cosine, and the angle at f is 52.08 degrees. Part B 2a. This is the ambiguous case. We are given two sides and an angle that is not between them, so two different triangles can fit. Here is the original with a sharp angle at f. Keep that in mind, and let's find the angle the two triangles share. Use the cosine rule once more, this time for the angle at h. Put the three sides in, with the angle at h between m, h, and h, f. The angle at h comes out as 31.13 degrees. The second triangle keeps the same two sides and the same angle at h, but the angle at f is obtuse instead of sharp. Its obtuse angle is just the supplement of 52.08, which is 127.92 degrees. So we sketch it with a straight edge, h prime at the left, the obtuse angle at f prime, and m prime up to the right. The two known sides are root 142 and root 61. Part B 2b. We keep this alternative triangle and finish it off. To get the top angle at m prime, we confirm the angle at h prime with the sine rule. The sine rule pairs each side with the sine of the angle opposite it. The side root 61 faces the angle at h prime, and root 142 faces the obtuse angle. Solving gives 31.13 degrees, matching the angle at h exactly as required. The three angles add to 180, so the top angle at m prime is 20.95 degrees. Now the area. The two sides we know meet at m prime, with the angle we just found between them. So we use 1/2 times the two sides times the sine of the included angle. Putting in the two sides and the sine of the top angle, working it through, gives an area of about 16.64 square centimeters. So, to recap, in part A we derived the cosine rule for m, h, the angle at f is about 52.08 degrees. The alternative triangle is obtuse, with its wide angle at f prime. And in that triangle, the top angle is about 20.95 degrees, giving an area of about 16.64 square centimeters.